L'Hopital's rule. L'Hopital's rule is used to get limits, to find limits of functions that have an indeterminate form. L'Hopital's rule states, if f of x is g of x over h of x, and the limit as x approaches a of g is the same as the limit as x approaches a of h, and they're both equal to 0. In other words, then the limit as x approaches a of f of x, in other words, if you substitute 0 over 0, is equal to the limit as x approaches a of the derivative of g over the derivative of h. L'Hopital's rule also works if these two limits go to infinity. So if we have the limit of something and it's an indeterminate form, 0 over 0 or infinity over infinity, we can use L'Hopital's rule. Just notice, it's not the derivative of the quotient. It's the derivative of the numerator over the derivative of the denominator. We'll see some examples. Let's say we have the limit as x approaches 0 of sine of x over x. We substitute 0. Sine of 0 is 0. X is 0, so it's an indeterminate form, 0 over 0. So we use L'Hopital's rule. Sometimes you want to indicate that you're actually differentiating, so you can put like a derivative, like an apostrophe on top of the equal sign. So we have the limit as x approaches 0, the derivative of sine is cosine, the derivative of x is 1. Now we try substituting, cosine of 0 is 1, and 1 is 1, so the limit is 1. That would be the answer. Let's see this other one. The limit as x goes to infinity of x cubed minus 8 over e to the x. Right. If x goes to infinity, x cubed goes to infinity. E to the infinity also goes to infinity. So we have infinity over infinity. We can use L'Hopital's rule. Take the derivatives. The derivative of x cubed is 3x squared minus the derivative of 8, 0. I'm not going to put it. And the derivative of e to the x is e to the x. Now I try evaluating. If we substitute infinity here, 3x squared goes to infinity. So it's infinity over infinity. So we do it again. Find derivative. Derivative of 3x squared is 6x. Derivative of e to the x is e to the x. Again, 6x goes to infinity as x goes to infinity. E to the x, it goes to infinity. So we do it again. Derivative of 6x is 6. Derivative of e to the x is e to the x. So we have 6 over infinity, and that is 0. So this limit is 0. We have other indeterminate forms. Remember, those are the ones that you cannot determine just by looking if the limit will be a number or infinity or undefined. So these are the two that we know, but this one is also an indeterminate form. It depends on how fast is the value getting to 1 and how much is it increasing. Because we know that if it's greater than 1 and you multiply it by itself a lot of times, it'll grow and grow and grow. But if it's less than 1 and you multiply it by itself a lot of times, it'll decrease and decrease and decrease and basically become 0. So that's an indeterminate form. So is 0 to the 0 power. If you get the form infinity to the 0 power also, and even infinity over infinity. Sometimes infinity over infinity will go to 0. Sometimes it'll go to a number. Sometimes it'll go to infinite or negative infinite. It really depends on the infinities. So these are all indeterminate forms. And we can use L'Hopital's rule for finding their limits as long as we can rewrite them as the first two, as a quotient. So if we can transform any of these into 0 over 0 or infinity over infinity, then we're good. Let's see this one. The limit as x goes to infinity of x to the negative 2 over times e to the 2x. Well, this has the form of infinity to the negative 2 is 1 over infinity squared. So it's 0 times e to the infinity is infinity. I guess I missed that one. Yes. This is the other form. 0 times infinity. Sorry about that. And it's one of the forms. So if we can transform it into 0 over 0 or infinity over infinity, we're good. This one's really easy because of the exponent negative 2. I'll write it as a positive exponent. It becomes e to the 2x over x squared. And the limit as x goes to infinity of that, that's infinity over infinity. So we can apply L'Hopital's rule by taking the derivative. The derivative of e to the 2x is e to the 2x times 2. And the derivative of x squared is 2x. So we have that. To simplify, to find the value, I'll cancel the 2's. And that's infinity. X goes to infinity, so it's infinity over infinity. So L'Hopital's rule again. The derivative of e to the 2x is e to the 2x times the derivative of 2x, which is 2, that's here, just like before. And the derivative of x is 1. So as x goes to infinity, this is 2 times infinity over 1, that's infinity. And that would be the answer. Let's see 2 more examples. The limit as x goes to 0 of 1 over x minus 1 over sine of x. Okay. 1 over x takes the form of infinity. 1 over sine of x as x goes to 0 is 1 over 0. So this is infinity minus infinity. Okay. In order to use L'Hopital's rule, need to transform it. Again, very easy this case because you just put a common denominator. Makes it a single fraction. The common denominator is x times sine of x. Got it here. X times what is x sine of x? Is sine. So 1 times sine is sine. And here this one's missing the x, so multiply times x, we have that. If I try substituting now, I got sine of 0 is 0, minus 0. So 0 over 0 times 0, 0. Perfect to use L'Hopital's rule. So now I'm going to differentiate here. The derivative of sine is cosine. The derivative of x is 1. And this is a product. Derivative of a product. Derivative of x is 1 times sine. That I got here. And then x times derivative of sine, which is x times cosine. If I substitute now, I got cosine of 0 is 1, minus 1, that's 0. Sine of 0 is 0, plus 0 times 1, it's still 0. Differentiate again. Derivative of cosine is negative sine. Derivative of negative 1 is 0. Derivative of sine is cosine. This is a product, so derivative of x is 1 times cosine, plus x times the derivative of cosine, which is x times negative sine. Now this is 0. Cosine of 0 is 1. Cosine of 0 is 1, so this is 1, 1, and this is 0. So it's 0 over 2, which is 0. One last one. Very interesting one. We got a exponential function, really a variable base and a variable exponent. The limit as x approaches 0 from the right of sine of x to the power of x. That's the limit I want to find. And if I substitute, I get 0 to the 0 power. That's an indeterminate form. Now, in order to make it a fraction, I'm going to use a little trick. I'm going to call this p. What I want to find out is what's p. The limit is p. But to make it a fraction, I'm going to use logarithms. I'm going to take the natural logarithm of p and the natural logarithm of this limit. So the natural logarithm of p equals this. Properties of limits, I can have this natural logarithm move in front. So that's the limit as x approaches 0 from the right of the natural logarithm of sine of x to the power of x. Okay. Properties of logarithms now. This sine of x can go in front. So I got the limit as x approaches 0 from the right of sine of x times natural logarithm of sine of x. If I substitute, this is 0, and this is natural logarithm of 0, it goes to negative infinity. So it's 0 times infinity. Okay, need to make it a fraction. I'm going to put this in the denominator. So that's the limit as x approaches 0 from the right of the natural logarithm of sine of x over sine of x to the power of negative 1. So now I got infinity over 1 over 0 infinity. Okay, I'm going to apply L'Hopital's rule. Derivative of natural logarithm of sine is 1 over sine times cosine. Derivative of the denominator is, well, negative 1 times sine to the negative 2 times the derivative of sine, which is cosine. You can simplify by canceling the cosines. So I got 1 over sine. So this limit is the limit as x approaches 0 of 1 over sine. Instead of dividing, I'm going to write times the reciprocal of this. So it's negative 1 over, sine squared over negative 1. Well, the square can cancel the sign. 1 over negative 1 is negative, so I got negative sine. The limit as x goes to 0 of negative sine is 0. So the natural logarithm of p is 0. But I don't want the natural logarithm of p, I want p, the limit, the original limit. Well, this is in logarithmic form. Let's put an exponential. The base is the number e to the power of 0, and that's 1. So the limit as x approaches 0 from the right of sine of x to the power of x is 1.